Hello everyone, and welcome to part 4 of our Industrial Warehouse Design Series lectures, in which we are going to be talking about the design of portal frames. Once again, this material is based on the steel construction info, especially part 4 in a multi-parter, which says single-story steel building design, and I'm talking about part 4, which is the design of portal frames. So whenever I say the reference in the video, I'm referencing this part. So of course, today we're going to cover some talk about the analysis in the ULS, the SLS. I am not going to cover much about the stability, but I will refer to it at the end and talk a little bit about it during the video. And of course, the design of elements, and secondary components and other considerations. So the stability here will just be mentioned. I will not cover it in detail. Also further mentioning here is that this video lecture is part of a tandem video series that basically talks about the theory and the modeling application in robot. So robot structural analysis professional, and we are basically showing one lecture or two in theory and one lecture or two in robot, and the video list and the playlist that basically shows those videos sorted is going to be linked on the top right here. So take a look on that if you want to get a bigger picture of what we're doing here. With that being said, sit back, relax, and enjoy the show. Alright, so when you deal with your ultimate limit states, you have two possibilities for analysis. You have an elastic analysis and plastic analysis. Now I know that the ultimate limit states happens when material starts to fail at the ultimate stresses, which means you are way beyond your yield stress. But as we'll know during this video lecture, the Euro code as well as the American codes actually allow you to use the elastic analysis and design using those results in the ultimate beyond yielding stress range. So that's good. Now the elastic analysis is basically what we deal about in our everyday life in Autodesk Robot. If you have a plastic analysis, you will basically take a look on the plastic hinge formation, and this happens usually at points of max moment. This could happen here in the rafts, because here you have max positive moment. This could happen in the column here, and it could happen in the raft here, by the way, rafter, because here you have maximum negative moment. You would think, but doctor, why don't I get the plastic hinge here in the rafter? You don't get it here because you have the haunch that increases the strength of the rafter. Similarly, you don't get the plastic hinge in the column here because once again you have the haunch that increases the strength of the column. So the weakest point in the column with the highest possible moment is basically this point, and that's the position of a plastic hinge. Also, the weakest point in the rafter with the maximum moment is this point, and that's where you get a plastic hinge. Of course, you might get a plastic hinge in the negative side, which is this place, but I mean, usually your positive moment is higher, so usually this develops before this. But in theory, you should have both defined as plastic hinges. Now, I have been talking about plastic hinges in my robot series. There is a video about how you can define plastic hinges. I will link it above, so you should take a look just to understand how softwares deal with plastic hinges. Now, of course, here I put my plastic hinges in a symmetrical way. This is usually not the case because in reality you have a horizontal load here that could happen either because of stability issues, of wind load issues, or because of geometrical imperfections. And this horizontal will actually change the moment distribution and cause those hinges to basically exist in addition to the hinge in the rafter here that is not drawn. So this symmetrical hinge is not really realistic. This is more realistic. Another thing to explain in the ULS limit state is the base stiffness. Now, you could assume a pin at the base. This means that you would have theoretically this at the base, which is kind of odd because usually your support is between the pin and a fixed support. It's not 100% pin and it's not 100% fixed, but well, it's the decision of the modeler as well as the details of the steel that will basically shift the assumption from between pin and fix. That's something I will leave for the engineer's discretion. But still the code basically, and even section 3.4.4 in the reference suggests that you may, it's not a must. You may assume some spring stiffness in your pin like a pin with a spring stiffness, and you can use 10% of the column stiffness when you calculate alpha critical and alpha critical established. And this is something about stability and second order effects. That's in the part 4. I will not be dealing with it because I will rely on the elastic analysis. So this is not going to be covered by me. And you can use 20%. You don't have to, but you can use 20% of the column stiffness for deflection calculations when you use the SLS load case combinations. Column bases with a thin base plate and 4 bolts are considered nominally pinned according to the reference in some countries. In fact, although they do carry some moments, that's what I said about the gray area. It's not 100% white, it's not 100% black. You are usually in a spectrum between being pinned and being fixed. What about the SLS and deflection criteria? We have 2 deflection cases. The first deflection is a horizontal deflection, and the second deflection is a vertical deflection. As for the horizontal deflection, the Eurocode basically doesn't say anything. It says it's about the client and the national annex. So well, we check the national annex. Germany has nothing. Spain, for example, says that the portal frame without fragile elements susceptible to failure in the envelope. So there is nothing that is dangerous on the facades and the roofs. If you don't have anything fragile on those things, then you have H over 150. So if your H is 8 meters, then your maximum displacement is 50 millimeters or 53 millimeters, which is kind of cool. Of course, if you are under fragile loading, then this becomes immediately half of it. So it becomes 26 point something millimeters. Good to keep in mind, but just you can see that some countries just don't care about it, like Deutschland, and some countries care about this. It's the horizontal displacement after all, so it's really a difference here. I will just keep this tabbed in my mind that I should, hey, for our H eaves height 8 meters, I will have 50 millimeters in my head just to keep the deflection in check. How do you resist that? Well, basically by increasing the strength of your columns. All right, going on, you have the vertical displacement. And once again, the code here tells you that it's either client or national annex. For example, in France, it tells you it's L over 200. Now, W3 is something else, and I wanted to read it in the reference. I'll just keep it as L250 or L200. For portal frames, I'll just take it as L200. So if my portal frame is, I think it was 30 meters, right? I think my portal frame was 30 meters in the robot series. So 30 over 250 will give you, oh, that's a lot. It will give you 120 millimeters. So I should keep this in mind that my displacement is maximum 120 millimeters. Well, there are cross-section types about resistances. There are 4 classes of cross-sections. Now for the American code enthusiasts, in the AISC, those are basically called compact sections versus non-compact sections. In the Eurocode, it's a little bit different. You have 4 types of sections. This means basically that class 1 will rotate really high, has high rotation capacity, and will reach moments higher than the plastic moments. It will reach thetas way beyond the theta required for fully plasticization. Now, I know for the MSc and PhD people, they would immediately say, wait a minute, there is no moment higher than moment plastic. And you are right. If you have a perfectly elastic, perfectly plastic material model, then indeed MP is your upper limit and you will not be able to produce any extra stresses from further plasticization. But if you use strain hardening, then yes, you will be able to create more stresses even after the point of full plasticization. And exactly this is what you see here. Of course, this is really high and advanced, but well, I just wanted to mention this just in case I have MSc or PhD or even instructors watching this, that, well, we know that it's much more complicated than this. Anyway, class 2 will allow you rotation, but when you rotate the beam or the element more than what is possible, it will drop down back to moments below the plastic region. Finally, now in class 3, you will never reach the plastic moment. This is a non-compact section, by the way, in AISC. Because you will have basically buckling, local buckling in the flange, for example, before you can fully plasticize the flanges. Of course, class 4 is total waste. Here you will not even reach the yield moment, and to be honest, I don't know why those exist, but I guess that exists. For AISC fans, as I've said before, this is similar to the compact classification we have here, and the code actually says if you want to use plastic analysis with plastic hinges and so on, your elements should be class 1, meaning that they can rotate enough. Okay, for the rafter design, well, there is of course usually the ULS controls and the SLS is checked. The design is according to the Euro code, needs to be checked, and the softwares do check this for you. You have two places, you have hogging moment here or negative moment here, and you have sagging moment here or positive moment here. Of course, in the hogging moment, in the negative moment, then you have to stabilize, and that's what you talked about stability here. You have to stabilize your rafter, especially in this domain where you have negative moments. You have to provide stability for the rafter, and of course you need to provide stabilization for the column at the place where the haunch hits the column, because the haunch will have axial forces. It will hit the column hard at this point, and if you don't stabilize it or just add some extra strengthening elements or plates, then it will buckle here and will cause all kinds of problems in the load carrying capacity. You should read it, you should read this. It's really cool to be read, but I just wanted to give you the gist of it. Stabilization can happen for both beams and columns by means of this. You can see the connection here. In case of column or beam, you can stabilize both beams and columns by using the purlins and connecting a bar, a stabilization bar between the purlin and the far end of the beam, just to stabilize it against negative moments. Because in positive, your compression is on top, so the purlin is very effective in stabilizing the beam. In negative moments, your compression is in bottom, and you need extra stabilization to stabilize the lower flange in compression. Also, you have those tie rods or eaves beams. Those are used in the eaves to basically hold those together. And you can also have some stabilizations for the column. It's kind of good to read. I'm here only to show you the gist of it. Column stabilization and rafter stabilization look the same. What about bracing? I have done this in Autodesk already, but the reference gives more details. You can single brace, V-brace, cross brace, and even use a fully fledged moment resisting frame. Of course, I am more a fan of those stabilizations. I'm not a fan of using a fully fledged moment resisting frame. Why? Because it will cause all kinds of complications here. I mean, in this connection, think about it. You already have a moment resisting connection here, and now you are asking for a moment resisting connection perpendicular to the page. I mean, this will become a Swiss cheese of a column because you're gonna fill it with holes. And I think this will cause all kinds of problems. So I am not really a fan of stabilizing the longitudinal direction with frames. I'm not a fan of it. I'm more a fan of using such stabilizations that actually help. Of course, that's just a suggestion. Feel free to do whatever you want as long as you can justify what you're doing. So those are the options of stabilization. You can select any one of you want. Another stabilization that you should take into account is when you have a crane or you have some beam here in the center. If you have a crane or beam, assume you have a crane here. Of course, if a crane moves back and forth and you have some sort of load being attached to that crane, like some sort of heavy lifting, then of course when you start moving you have an acceleration, and when you stop moving you have an acceleration. This will shake the entire warehouse left and right, and you need to provide proper X cross bracing stabilization at the beginning and at the end. And notice it's being connected at the crane girder level. So that is kind of cool. Of course, our dear subscriber Donald Khani was asking, what happens if I have a long column? Should I brace it more than an X bracing, like double X bracings, or is it an overkill? Well, you can double X brace it, and even if your column is short and you have a crane, the reference tells you should cross brace it because you want to reduce the amount of vibrations and increase the ability of the structure to resist the accelerations that happen because you are starting or stopping the crane. Of course, this all happens if your crane is integrated and being carried by the portal columns. How are those bracing used? Those are usually like hollow tubes being connected like this to a column. This is the external purlin. You can see the bracing being connected to the column, not in the same plane of your external bracing. So offsetting the bracing was actually a correct call we have done before. This is the roof bracing. Notice something important, that if you have gable columns, your bracing should connect to the gable columns. I had a nice comment of one of our subscribers and viewers who mentioned that some cool suggestion to how to use the roof bracing with the gable and release some of the purlins. I will show it here. You can pause and read. I think that's also a possible idea, and that's exactly what CE is all about. The idea here is not only just for me to give lectures, but for me also to create a community of engineers who share and care. And you can see this is being successfully happening here, so I'm really happy about this. Of course, feel free to read his comment and pause the video. You might find some really cool ideas beneficial here. I will stick to the reference, but I think such a comment is really cool. Now, what about gable frames? There are two options for gable frames. Option number one, which I personally like, but the reason why you see P and then double zeros and then distance and rows is because my little kid, my baby CE, actually climbed on the desk and started bashing, I think, values. So you see this. This is basically baby CE. Option one is basically that you use the portal frame. Perfect, like you have a portal frame and the gable columns do not support the rafters. They are just standing and they don't support the rafters. Why is it cool? Because you can have the same portal frame design for all portal frames. That's one. Two, because you can easily extend the structure in the future because you have designed your portal frame without taking the gable into account, which means you can easily remove it and basically continue your life, no problem at all. And of course, in that case, you need, of course, to have a fixed support at the bottom of the gable, not a pin. And you have to basically cross-brace the gables together if you want to do that. Or you can actually, for example, if you have a gable frame like this, you can actually have a secondary frame with full movement action, 1, 2, like this, with a beam, a gable beam, another beam like this maybe because you have another opening, and you will have to realize a full frame action just for the sake of stability. And yeah, I think it's kind of cool. That's one option. I'm fond of it. A second option is, well, to consider the gable frame supporting the rafter. That's another option. In this case, you would have a simply supported rafter. See, there are options and you can use any one of those. I will choose the option where the gable columns do not interact with the portal frame. You may disagree with this. It's up to you. I just use it for simplicity reasons. So yeah, well, those are options, right? With that being said, we go to my favorite part, the connections. Now, some of those I've covered before. Of course, here you have the eaves connection where you have the haunch. This is the rafter, this is the haunch. And sometimes here you have a strut opening for the strut that connects the eaves, and that's perfectly fine. This is the apex with an increasing stiffener haunch here to increase the moment arm of the bolts. I've talked about this before. You have base plates for large columns, base plates for small columns. You even have sometimes pinned base plates and fixed base plates. Some people like to call this a fixed base plate, but of course here then you must make sure that those bolts are able to resist moments enough for it to be called fixed. Also, you must make sure that this doesn't rotate. Of course, this is definitely a fixed support because you have those stiffeners which will definitely make sure that this thing doesn't rotate. Of course, I told you that this is a spectrum between pin and fix, and it's your responsibility to basically assume those correctly. So finally, the reference says that, well, the steelworker's contractor is usually responsible for those details, and it must be clear in the documentation who is responsible for this. For base plate, furthermore, you need to resist horizontal movements. This can be done via multiple things. You can check the passive earth pressure, and this is something I will not do in Autodesk Robot, but this is a check you should do. You can check if, well, the passive pressure, which is basically K passive multiplied by gamma multiplied by H. This is the pressure here, and you have to multiply it by, you have to sum it up by a triangle. You need to make sure that the passive air pressure is enough to hold your horizontal reaction. If it's not enough, there are two options. Consider a deeper base concrete block, or basically hold it in place by something like this. Or you can even, you can think about it. There are multiple solutions for this. Usually, the role of a civil engineer is basically to provide the calculations, and there is a unique drafter who draws those things into AutoCAD drawings. But of course, maybe you need to do it yourself. So at least now you have a database of details you can use. What about secondaries? Well, secondaries like the eaves, beam, or strut, those are the details of the secondaries. Furthermore, like the purlins and so on, just check it out. Those are secondaries, as the name suggests. Usually when you have a big project, you have all those AutoCAD drawings, and the last drawing is like generalistic detailed drawings with details in it. And basically you can just redraw this and change the values if you need to use them. Other topics that I will not cover today is plastic hinges, stability of frames, and stuff like fire resistance. I'm not covering those. The idea is that you should read them yourself and, well, I mean, look, let me show you why I will not cover those. Let me, for example, talk about the stability of frames. If I want to talk about the stability of frames, one issue that is mentioned here is snap through. Let me show you why I don't want to talk about those topics by talking about the snap through. What is the snap through stability of a frame? Well, the idea of a frame or a truss snap through comes from something called the geometrical nonlinearity, and you can read a lot and understand this if you check out something called a von Mises truss, example for snap through in von Mises trusses. The idea being is that while you are increasing the pressure, the point goes down a little bit, increase the force more, the point goes down more, until a point where suddenly everything snaps and your entire truss flips to the opposite direction. Instead of you having compressive forces inside the truss elements, now you have tensile forces inside the truss elements. This is of course a type of instability because you will never have it. You should never allow this to happen because of all the destruction you will cause to the stuff that is being hanged below the roof. Also people will evacuate when they see this. But the idea being that, hey, this instability exists, snap through, you should double check it. Why am I not going to double check it? I'm not going to double check it because my rafter angle is at least 6 degrees, which will basically give you a 10% slope, meaning if you have a portal frame of 20 meters, span, then the difference between the eaves and the apex is 1 meter. And I don't think you will have a deflection that goes all the way down to 1 meter. So that's the reason why those are interesting, but I'm not covering those. That was a quick rundown on all the design aspects of portal frames. So with that being said, we want to continue this in our robot part. Before I finish, of course, I want to give a huge shout out to our dear channel members whose names are going to be shown on the screen. I would like to thank them from the bottom of my heart, as their contribution to the channel helps us basically provide you with those videos. So thank you very much. Once again, of course, if you have enjoyed the video and you found it beneficial for you, then please like, share, comment, and subscribe, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.